Welcome back, everybody. We have a special guest introducing today's focus.
Hello, chat. If you're just joining us here today, calc is short for calculator, not calculus, calculator. Thank you.
Cool. Fantastic. The more you know. Cool. So, here's my graph. I plotted it. Now, not everybody had it. That's okay. This purple line on my graph is representative of what? The asymptote. Now, remember, we introduced a whole new way to break functions or domains of functions yesterday. We had seen before, can't take square root of a negative. I mean, we can, but it's not real at that point. Okay, doesn't work. That's an asymptote. Or undefined spot. You can't divide by 0. That's an asymptote. Last one that we added yesterday. The argument of a logarithm, it must be greater than what? I don't think it has to be greater than 1. 0. Now, when we're looking at this, the vertical asymptote is always going to come from when we set our argument equal to 0. Everybody can do this in your head. What's the argument of this function? Time out, pretend I didn't ask it yet. What's the argument of this function? Can you set that equal to 0? When you have x plus 4 equals 0, what do you get for x? Hey, look at that. That's our asymptote. Easy. Piece of cake. X equals negative 4.
Why is it 11 over 3 instead of 1 over 3?
So let's check. We'll go back into that.
Because I just didn't even notice.
Yep, that's okay, because we'll figure it out. Now, looking at it, the question that I had just now, we'll come back. Why 11 thirds instead of 1/3? Easy to answer, but it's easy. Like, it might take a few times to get it to click. Let's deal with the domain. Looking at the graph, domains are easier from a graph, I think. Maybe not. I don't think they're easier. It's the same. What values of x do you use? Do we ever use negative 4? Now, when I say which ones do we use, these are the 3 explicit points that I've written down, but are there more points that I just didn't put on there? How many points are on this curve? Infinitely many of them. What's the furthest left point you could possibly choose? You get arbitrarily close to it. That's a better word language.
3.999.
So 3.9 repeating forever, right? Negative 3.9. Or arbitrarily close to which number? 4. Do we ever actually touch negative 4, though? So when we're looking at the domain, you guys seemingly prefer interval notation. I'm going to use this one. X such that, what do you guarantee x has to be greater than? Piece of cake. Now, there's an easy way to do these, which, I mean, that is the easy way, but I'll make sure that it's like detailed and saying, oh, this is really how we do it. What about the range? How low does it go? Infinitely far. Negative infinity, right? What about how high does it go? Positive infinity. This is a weird idea because it looks like it's slowing down. It is. But does slowing down mean stopping? No, you can slow down how fast you go upward to be really, really slow, but if you let it go forever, it still goes up really, really high. So, easy way to write the domain, or the range, I'm sorry. All the way from negative infinity to positive infinity. All reals. I'm going to be a little bit more formal with it. X such that x is in the set of which numbers? The reals. This is the formal way. You guys can just write R. I'm okay with that. Cool. Now the question at hand. Remember, I advise you to choose values that make this easy to calculate. For the record, any number greater than negative 4 would work for this. However, when I'm looking at this, I'm always going to set my argument equal. You don't need to write this in because we have it. But to pick the points for a log base b, what do you want the argument to be equal to? 3 values every single time. 1, the base, whatever it is, and the last one, 1 divided by the base. Now, in doing this, I encourage this scratch work that I erased, but I encourage the scratch work to do this on the side so we don't have to try to think about it and get goofed up while we're building our table. The cleaner your table looks, the easier it is to take that data and put it on a graph. As we look at this, what is the base of this log? 3. So, what's the argument? I'm going to get the x values that I pick by doing the 3 following equations. I need x plus 4 to equal, what's the base again? 3. I need x plus 4 to equal, what's another choice that I always want? 1, and the last one is x plus 4 equals 1/3. Now, the entire argument. I can't just pick x to be 1/3 because that would make it 4.33333333, right? Okay, quick question. 3 to what power is 4.33333? I don't think so. That'd be 3 to the negative 1 is 0.3333, not 4.33. Like, it sucks. We can't do it. So if we do this, we get an advantage. Each of these equations is easy to solve. How would you subtract? Dang it. How would you get rid of this 4? Okay, so I'm going to subtract 4. And then on this side, I'm going to think of it like this. Is that still 4, though? What's 1/3 minus 12/3? Negative 11/3? Which means if I pick negative 11/3 for x, guarantee it's going to spit out this into the argument. That's why we chose it. I want this to be 1/3, not the x. Okay. Log stuff, feel okay. All right. We commented on it. I commented on it yesterday. You do not have to write this down, but there's one property that I think feels unnatural with log stuff, and a property that we've used. You guys have fond memories of proof. Makes sense. Everybody loves proof. We're going to look at a quick proof. That looks so small, but that's all right. You do not have to jot this down, but I do want to make sure that you can see proof is not this big scary idea, and it's not necessarily challenging or set up the way that you did it in geometry. I'm just going to remind myself, if I say that y is equal to log base b of x, log, not lob, log base b of x. This can be written in exponential form. This is true if and only if what? What's the base? So careful, be b here. And to what power? Just looking for the definition of a log. B to which power equals what? That's what everybody wants. That's a gut feeling, but it's wrong. B to the, not x, y equals what? X. Okay, so here's what I want us to think of. The one weird property that just feels like you just have to trust me. We don't have to just trust me, and I want you to see how easy a proof is. We made the claim yesterday, and again, you don't have to. Whoever's that is, will you go check? Because it's very loud. Oh, it gone. Okay, I want to show this. If I take a to the power log base a of x, does anybody recall what this is? Check your properties. So this is an exponential with base a, right? And what's the inverse of an exponential? The log. So when I take an exponential to its inverse, what should fall out of this? X. I want to verify that this is true, because kind of seems like you just hand wave and say, trust me, it works. But we don't have to just blindly trust that it works. We can work this pretty easily ourselves. Okay, so if I want to think about why on earth this works, let's just play around with it for a second. So this is a proof, but it's a really straightforward and easy proof, I think. Man, thoughts? Like, where would you even start? It's kind of ugly, right? So let's just try something out. Do you agree that I could suppose, and this is an assumption which we're allowed to make as long as we can show that it leads to the right conclusion, and this is a very different looking proof than you guys have done. I don't know what log base a of x is, but it's probably equal to something, right? Could I say that this is equal to y if we wanted to? Everybody okay with that? Like, I'm just saying it's a number. Which means we could now say that, man, this becomes a to the y equals x. Everybody cool with that? Like, nothing too crazy going on. Everybody agree? If we look at what we're trying to show, man, well, let's just think about how this is going to work. This looks a little bit nicer. Would everybody agree? But by definition, let's just see what we have. By definition, we have that y is equal to log base a of x. We have that written. But more specifically, we already have a to the power of y is equal to x. That's just this definition, right? And we're just expanding it. I can see by the blank looks, we're going to try this again in like 2 days. We're going to pause here. If you're writing it down, just save it. We're going to come back once we're a little bit more comfortable because I can see that maybe nobody's following and this is not super beneficial right now. Pause here. We'll be back. Okay. Do not let this deter you from the idea of proof. A little bit more experience will be good.
How much space do we need? Should we like...
This is where my conclusion is going to go. We're like one line away, but I can tell by the looks on your faces that it's not meaning anything. It happens. Cool. All right. We'll be back to this. We're going to hit it again. Now, beyond that, yesterday we did the graph of a log. Should we warm up with a couple log evaluations? Okay. So here we roll. Example. Let's graph another one. It's going to go quick. Graph log f of x equals, sorry. Ooh, should we get real crazy? Negative log of 2x plus 5 minus 1. Looks hard. Maybe it's kind of hard. Do we want to use base 10? Or do you want me to add a different base? Cool, let's just keep it like it is. This is log base 10 if we don't write it, also known as a what log? Not natural. Common. We'll get to the natural log here in a minute. All right, so check it out. You do not always have to do this, but we're going to go back to calculator game because I'm not doing a great job of calling on everybody all the time, as we should. Yes, the calc game, you might call it. Do y'all remember your numbers? Cool, cool, cool. And I will be number 13. Number 2. What's the argument? Okay, I'm going to pick this darker green because it's easier to read. Everybody agree the argument is 2x plus 5? Okay, so the terrible way to word that, because unless everybody says, yeah, I agree, then I'm not going to get the answers. Anybody opposed to this? Cool. Number 1, what is the base? Okay, this statement, you do not normally, like, these are all thought processes. You don't have to physically write this. We want x values that make argument, and I left some specific space there, equal to 3 things. Number 8, can you give me one of the 3 things I want to make the argument equal to? I don't have my list in front of me. I don't know who number 8 is. And you guys are writing, so I should probably slow down. Yeah.
Hi.
Hey.
Wait, can you repeat the question again?
What one of the 3 things I want the argument to be equal to? Why 2?
No, 0.
Why 0? Whatever you say, I'm going to ask why, just so you know. Man, I'm having weird time issues, and maybe I won't even notice if you have to flip your notes, or I encourage you to flip your notes. What? Say that again? It's kind of at the start. I guarantee we made the statement. I can find it on my notes as well. We want, if you look yesterday, when we graphed one, right at the beginning we said, hey, the vertical asymptote is at the x that makes the argument 0, and then choose x values corresponding to the base. Specifically, and we wrote it a moment ago, we want to set the argument equal to one of 3 things. And find this point in your notes there, Mickey. X values according to the argument, or to the base, we want to make it these 3 things. The base, 1, and 1 over the base.
Okay.
So give me one of those 3 values. So one of the 2, don't give me 1. 10. That's my base, right? The other one is, I'm just going to give it to us for free. It's 1. And the last thing I want it to be number 12. I need my sheet or people are just being quiet. Who's 12? All right, what's the last thing we want it to be? 1/10. Okay. Now, check it out. If I just pick x as 1, does it make my argument one of those 3 things? No, if I pick 1, it makes it 7. I don't want it to be a 7. I want it to be one of these 3 values. This is where my scratch work comes in. So I'm going to make different colors for each of these. Let's say we'll just do it in order. My argument is 2x plus 5. And the first thing we're going to do is set it equal to 10. Whatever x we get, I don't have to think anymore. When I solve this, that's the x that I picked to make my argument 10. Okay, that's what we're actually solving. What x makes this happen? So let's do a little math. Walk me through all the steps as quickly as you'd like, number 13. My pleasure. I'm going to subtract 5. And I'm going to divide by 2. I get x equals 5 halves. Now, I'm going to keep this over here before we build the table because I don't have to jump back and forth. We'll just do it all. Number 4, I also want my argument, which is 2x plus 5, to be equal to what? 1. Okay, I'm going to not do this one right now. And I'm going to leave a little blank space so that you can do that one. Last one, number 2. I also want to find 2x plus 5 equal to what? 1/10. These two parts are yours. I'm just going to put dot, dot, dot. And I want you to find me those x values real quick. As you're doing it, I'm going to get my table ready. Once we get these, just to check what we're doing here, and the order might come out wonky, just so you know. Like, it won't always go from smallest to largest. Depends on the situation and what order you do these in. But let's check it out. You're not allowed to think about it. Guaranteed, when I put 5 halves in here, and I'm going to just fill this in. Don't do math in your head right now. When I pick 5 halves, we've chosen that because it makes my argument what? 10. I didn't just do 2 times 5 halves in my head. I've already decided, not even decided, shown that it must give me 10. Okay, when we pick -2, and I'm actually going to be lazy with this, and I'll show some scratch work. I'll just leave it, but this way I can just do this. Gosh, technology's cool. Look at that. Okay, when I pick x as -2 without any additional thought because we've already done the work, what does it make my argument? We got -2 when we set the argument equal to 1. It makes this a 1 right here. Okay, when I pick -2.45 without any thought, I don't have to plug it back into my argument. We got -2.45 when we set the argument equal to what? This part is a huge time saver so long as you understand what's happening. I'm going to pause here for a second with full honesty. Somebody in here probably doesn't grasp it. I want you to turn to your neighbor and explain in similar, but probably not verbatim, why we've chosen these numbers and how we just saved a bunch of time. 30 seconds, pick one person to talk, explain why these are the x values we choose. Here we are. This question always seems tough when we do it. I have negative, and I have the right color. What's log of 10? 1. How would you phrase that question to make it a little easier to think about? That's how I think about it. If you guys didn't hear it, 10, our base, to what power gives me 10? 10 to the power of 1. So check it out. Here's what this becomes. -1 minus 1. What do we get? Sweet. Is this log hard to evaluate? Right here. I have a negative, and how do you evaluate this log?
What?
Go ahead.
I don't understand how you're getting -1. Where's that -1 come from?
This one right here?
No.
This one?
Yeah.
So it's going to show up here, and then it'll apply here as well. This statement, when you try to think about log of 1, how do you think about it? How would you evaluate what log of 1 is?
I'd use a calculator.
So if you don't want to, or you shouldn't, because we're going to pick nice values every time, check it out. What's the base here?
10.
So 10 to what power equals 1?
0.
Check it out. This whole log is 0. The value of the log is what power do you need to get that to happen?
Okay.
What's -0 minus 1? -1. Follow up, what's +0 minus 1? Still -1. Cool. All right, last one. 10 to what power is 1/10? -1, right? 10 to the power of -1. So -1 goes inside my parentheses. That's replacing my log. What's minus a -1? Positive 1 minus 1 is 0. Okay, we have gotten all the info that we need to graph this and graph it well. Only one little thing that I'm going to add to this. Do you want to physically graph it, or is this sufficient? Okay, so I'm going to do this without graphing it then. You guys do have to graph on your assignment tonight, just so you know. The vertical asymptote. How do we find it?
Set the arguments in the arrow.
So here's our scratch work, and then I guess I'll do the scratch work first. Why would I scribble it? I have an eraser. Okay, here's my scratch. And I'll just scratch. Shh. Okay. Blood pressure growing. Here we go. My argument is 2x plus 5, and I know that it equals 0 is going to be an issue. Help me solve it. Subtract 5, divide by 2, yeah? What do we just find? This is my vertical asymptote. Okay, and we can graph it if you want to. I just think you guys can plot points. Here's the bigger question. Without the graph, sometimes this can be hard. I want to know the domain and the range as well. It's so much easier than you think. I guarantee it. But we should graph. Should we? You could plot these points, right? Sketch it. Sketch it for me real quick with where we're at. And we're going to, you'll see why I've made this change. Rough sketch. 3 points. Eyeball them. I'm fine with it. Sketch this graph. I'm going to give you a head start. So I put those 3 on, and here's this asymptote showing up at negative 2.5. I'm just going to eyeball it. We'll get close and not touch it. Now, there's something fundamentally different about this graph than the one that we did a minute ago. Is it still a curve shape that blows up or to infinity or negative infinity? I'm not asking which infinity, but does it still blow up somewhere seemingly? Is there a curve that goes through these? Okay. As we're looking at this then, it's upside down to the other graph, right? Why?
It's decay.
So be careful with decay. I'm okay with that idea because that's what we call that shape. But what about this equation specifically made this happen? This negative out front makes it reflect where? X-axis. What do you think this minus 1 does? Down 1. And then this one's harder to tell, but it looks like it's been moved to the left a little bit, which is weird because it's positive, but that's all right. Now, looking at this, the graph itself, if you can get to this point, the scale's kind of ugly with this one. That's okay, but we can see it. It works. Okay, beyond this, from the graph, is domain and range easy? Okay, but check this out. If we hadn't had the graph, does domain seem like a harder question? You should make an important statement within this problem, but so it shows up like when you're looking back through your notes. The domain is, and this is going to be true for every log that we do in here, the domain is always found as a set of x such that, and you're going to have to do a little bit of work here, but we always require that the argument is greater than what? 0. So when I do this, I like to save a little bit of work. We know the argument already, right? Watch how easy this domain question is when you take advantage of this. I know the argument greater than 0 is where my function actually works. What's the argument? And we need it to be greater than what number? Can you guys solve this inequality? Okay, so I'll do it step by step. First thing is I subtract 5. Then what? Okay? We've essentially solved it, right? Check out how handy this is. This is a requirement that we put on x. So why don't we just do this? It's a set of x such that that's true. There's our domain.
Why didn't you just do that from the first place when... Oh, you're just showing the scratch work again?
So sort of. This is to find the asymptote. The asymptote is the beginning of my domain. So they're certainly related.
So, but why didn't you just say, so the asymptote, so we can't touch that, and then put it in the graph?
So we can see it from the graph. 100% we can. But if we didn't have this graph and I said, hey, what's the domain? It's harder to tell. Yep. Because the other thing you have to be worried about is that there's probably something that could make a log look like this on the other side of it. So when you wind up solving that inequality, if there's something that does this, it'll flip with the negatives as you solve the inequality anyway. This is the easiest way to possibly write your domain. What do you think the range is like for every log we ever deal with? For sure. All reals. Cool. All right. Turns out we do the exact same thing again. Like legitimately the exact same thing again. So I'm going to go really fast and you guys are going to have like 20 minutes to work on stuff. Okay. Graphing logs seems okay, seems awful. Where would you guys put it right now? All right, big opinions in here. Feels all right? Does it feel any different than last year when you did it? Okay, so probably then. Guarantee you guys did it. I'm certain of it. I can't be certain because I wasn't there, so that's probably a poor choice. All right, so notice how much room I have left on my notes. Very little, right? That's enough. I don't need much. Here we go. We have been looking at logs. Commonly, because we're human beings with, on average, 10 fingers, we use a common log, right? There's a number that shows up way more frequently in nature and in modeling stuff than the number 10, though. A natural base for many different applications of exponentials. 1 is weird because, not really, because 1 to anything is. Yeah, so that, like, it does, like, obviously, if 1 shows up in nature, then base 1 must. But there's much better places. Euler, Leonard Euler specifically, crazy guy, did a lot of stuff. E. Check it out. Last section. And this is going to go super fast. So, last little piece. We need to talk about the natural logarithm. Okay. Infinite aura at, yeah, for real. I'm about to give away infinitely many aura. An infinite amount? I don't know the quantity of aura. At least a bushel. A bushel of aura at stake here. I made a comment the other day. I guarantee nobody wrote it down. Who do we have to thank for the development of logarithms? Euler did some work with it, but he followed somebody else. A French mathematician, John. What did you say? Is it Gautier?
It's the guy who makes the cologne that's like the naked dude.
Oh, John.
My asthma doesn't like cologne, so I don't, not my thing. That's right, it's John Napier. Okay, now you guys have seen the natural log, guarantee it. What's the natural base? And Huggins, you said it a second ago. The natural base, and it's a weird number, but it shows up everywhere, is...
I said it?
You said it.
What was it? 1?
No, after that.
Oh, E.
E.
I completely forgot.
Okay, this is the natural base. Now, the common base is 10. The natural base is E for an exponential and a log. If we expand out a little bit further then, if I said, hey, write me a logarithm using this base, it's pretty easy to say, oh, okay, it's log base E of x. Do you guys agree that's the same as log base 10? It's just this, I don't want to write 2.71828 blah, 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 forever and ever and ever. What's up? Okay, all right. Have you guys ever used log base E of x? Yes, you have, but we don't write it like this. Okay, John Napier, father of logarithms. I said he's from where? Okay, I do not speak French. You do not need to write this down, but it adds a little bit to see why. I don't speak French. There's probably an accent in there somewhere, I would assume.
Wonder what that could be.
Log de natural, right? I don't speak French. Oh my gosh. The log de natural is what we're looking at. Man, mathematicians are lazy. We do not like to write a bunch, which is why efficiency is such a big focus on like everything you do mathematically. Man, if only log de natural led to some like pretty easy and convenient notation for the natural logarithm. Your books don't do it cursive. My L's look like my 1's look like my I's. ln. Log de natural is where this comes from. ln, natural log. Log base e. They're all the same thing. Would you prefer to write log base e over and over and over and over, or just ln? And ln is short for what? Log base e. And in French, it's log de natural, which we have who to thank? It's not Jean-Paul Gaultier. All right. Cool. Now, turns out this is just a log with a base. E. Is E a number? So literally every single property that we've seen already applies to this logarithm as well. Exactly in the same way. I'm going to go really quick through these. Take out a calculator, at least one person. Grab your calculus. What's adjacent to the number 4, but it's not 5? What's right underneath log on your calculator? ln. And that's the what log? The log base e, or the natural log. So, looking at these, the only thing that gets uglier with this is two things. Okay. Do me a favor real quick. If you see evaluate the natural log and there's not an e in the expression, it's a calculator problem. I want to know what's the natural log of 6. Ken, what is it? So natural log of 6 is equal to 1 point, and this is just me writing this down, 1.77. Okay. 779? 79?
1.79.
Okay. Does it say 79? Okay. Did you realize I read it back to you wrong? So what should you do when you realize that? Whoa, quiet down, man. You don't have to shout. See, so that's the part. I'm not your bully, and I'm so sorry because that felt like it.
Yeah.
Like, no, I'm just messing with you. That felt mean. All right. So old jerk here, my bad. What does this mean? The fact that the natural log of 6 is 1.79, can you explain to me, like, what? Okay, I'm going to flip this question. What is e to the power of 1.79? That's all I'm looking for. Log base e. If we write this out, and it sucks to do it, but you can, I will never stop being mean about it if you do this, so just so you know. This is the same expression. This means the exact same thing, which is true if and only if, and we use the definition of logarithm, e to the power of 1.79 equals 6. It's just that back and forth between these forms. Now, some crazy stuff. Nope, we'll save that for the end. Cool. Awesome. Means we get some properties that we inherit for free. I can put it back.
Oh, okay. I didn't understand where it went.
Yep, I just get rid of it. Just because we don't really need it.
I see. My bad.
No, you're good. Okay, real quickly, properties. Here we go. We get some nice properties. What's funny, Binky?
We need to pee.
You need to pee?
Yeah,
Go. You're fine. Don't pop. Go. All right. You're going to have to get these properties when you come back, though. Check it out. We're getting crazy. If you want to look at the properties that you had the other day, you can. I want to know what is the natural log of 1. You can type it in, but you can do it without it. Think about what it means. E to what power is 1? Cool. All right. What's the natural log of E? Why? Because e to the power of 1 equals e. Cool. What's the natural log of e to the x? And this is always a weird one. X. Is that what you said? Love it, because e to the power of x is what you need to get e to the x. Okay? The flip side of this, what if I take e to the power of the natural log of x? X. Cool. So these are like the same property. This is just opposite directions. And the last one, I'm going to make the claim that natural log of x is equal to the natural log of y. If and only if, what would you conclude? the exact same properties come through with the natural log because it's just log based a number. Everything works the same. Graphing it's a little bit uglier because you have to deal with making the argument e, 1 over e and 1, and it can be ugly, but the exact same rules happen. Cool. You guys get 15 minutes. The assignment looks kind of long. I don't know how long it actually is. I'm going to give you an option right now. I have vocab on here. If you would rather, I'm okay to take the vocab questions off, but I'm going to call on 6 random people to answer questions. I lied. Just write them. Don't write the definitions, but write them. So check it out. Eventually we'll get there. Ta-da! Homework 3.2. Page 218. Do you want me to read you the numbers? Everybody's going to look anyway. Okay. Have we talked about circles at all in this process? Like, I haven't mentioned circles in a while, right? I'm going to show you guys one of what is considered the most elegant results in all of mathematics. Elegant in math just means you can write it nicely and cleanly and it's like pretty. It's also written on the backboard, but it's small back there. Do you need to go to the restroom too? Okay, tell them to hurry.
Hurry up, man.
All right, I'm gonna copy this and put it on the screen because I want you guys to see something. We're not gonna talk like in detail about it, but it's cool just to see the result. Somebody need some lead?
Yeah.
Okay, I cannot help you with your lead though.
That's okay.
All right, so check it out. There's our homework. Way out on a limb. What do you think we get if we take e and we raise it to the power of I pi? Like that conceptually is just wonky, right? It's 1. E to the power of I pi is 1. This is often considered like one of the most elegant equations in math. This is the work of Leonard Euler. It's crazy and it gets like weird, obviously. There's crazy stuff happening. It's a big deal in mathematics. Not to you guys yet, but cool. The rest of the time is yours. You guys missed the log properties. The same 4 properties that we got with every other log works with natural logs. Cool.